In this video, we'll talk about how we can infer the syntactic tree of a sentence using a recursive neural network. So in the previous video, we discussed how in the recursive neural network approach, we had the neural network which could merge the pairs of a pair of representations of different nodes in the syntactic tree and then output the representation of a parent node. And we also discussed that we, in that neural network, we would also have a part of the neural network which would also output a score for the quality of that merge. And what we'll see now is that we could use that score in order to score entire trees and then essentially search in the space of trees to find the tree which would be most appropriate as the best syntactic tree to explain a given sentence. And at which point it means that we can just perform syntactic parsing using a recursive neural network. So this is the neural net we saw before. It takes, this is the merging neural net, which takes representation of two children in a tree, representing either a single word or a phrase in that tree, and then outputs a merged representation for the parent in the tree. And then it also gives us a score for the quality of that merge as just a linear transformation of the merged representation. Now let's assume for now that this prediction score is actually a good score for identifying whether these two parts of the sentences, these two phrases or two words or pair of word and phrase were actually appropriate for being merged and be part of a more global syntactic tree. Now, how could we use that in order to assign scores to entire trees? And then how could we try to at least approximately search for the best tree that has the biggest score? Well, the simplest approach in terms of scoring an entire tree is to just assign it the score which is going to be the sum of all the merging scores. So essentially, the tree is going to be as good as the sum of the qualities of each merges that are required, that are done by the recursive neural network for that parsed tree. So for instance, imagine that we had the small sentence, the cat is here, and that we consider this particular parsed tree, then the merges we'd have to do is we'd have to merge the representation of the and cat to get the representation here, and then our merging neural network would also give us as the output a score which I'm calling S12, 12 because it's essentially scoring this subtree which merges 1 with 2. We'd also have to merge is and here. This would give us this word representation from phrase representation from these two word representations, and again we get a score for that merge. And then following this parse tree, you have to merge these two nodes to get the parent node for the full sentence. So we're merging this representation and that representation by concatenating them, multiplying by W, applying a sigmoid, which gives us this vector. And from that vector, multiplying by W scored gives us the score for that merge, which I'm calling S1, 2, and 3, 4. So we see that the index is essentially a representation with parentheses of the actual tree. That's the notation I'm using here. And then the score for the full tree is just going to be S12 plus S34 plus S1234 as written here. So in other words, the sum, the score of the tree is just the sum of all the scores I computed as I was performing all the representation merges as I was going up towards the root of the corresponding parse tree. Now, if we were considering instead this parse tree, then I'd have to merge the with cat, giving us this and this score here. Then I take that representation and this word representation, merging it to get the representation for the cat is, which is obtained by taking this representation here, concatenate it with this one, multiply by W, apply sigmoid, then multiply by W score, we get the score for that particular merge, and so on to get the score also for the merge at the root of the tree. And then this syntactic tree would have instead the score S12 S1, 2 with 3, and S1, 2 with 3, and then 1, 2 with 3 merged with 1. Okay. So now the question is, for a given neural net that performs these merges, so this neural network that with the W's and the W score and the biases as well, these are the parameters of the recursive neural network. It corresponds to the recursive neural network, really. And so for a particular recursive neural network, what is the tree that has the highest score? How do we find this particular tree? Unfortunately, we can't do this exactly. However, Richard Socher and his colleagues propose an approximate algorithm which they claim works well in practice, and indeed they report good results by using this particular inference procedure. So let's look at this inference procedure. I'm going to describe it essentially using an example to give you an intuition for how it works. So we want to find the tree which has the highest sum of all of the merging scores. And so because the sum of a bigger tree is going to, we can think of it as essentially, decompose it as the sum of the score associated with its subtrees, then that's essentially how we'll obtain an algorithm which will first look at the best subtrees and then move to trees that cover more and more words to eventually reach an inference of the tree which would cover all of the words. So specifically, we'll have an array, which I'm calling A here, which is indexed by the first and last word that the tree for this particular cell in the array covers. So for instance, this cell would correspond to trying to infer the tree that covers the words from position 1 to 3. So the, cat, and is. 2, 4 would be covering instead cat, is, here. And 1, 2 would just be the tree that covers just the and cat, and so on. And as we'll see, as I describe the algorithm, I'll be able to reuse, when I'm looking at the scores of the trees that cover 1 and 3, I'll be able to reuse these scores of the subtrees below in the array, and so this way I'll be able to reuse the computations that I've done for smaller subtrees to perform a maximization for larger subtrees. So let's first consider what is the best subtree that cover just 2 words, so 1, 2, and 2, 3, and 3, 4. But in this case, there's just one tree, the tree that merges the 2 corresponding words. So from that, we could then compute what is the score associated with each such subtree. So in this case, this is a score of merging 1 with 2, which could be computed using our recursive neural network, the part that merges the scores and then computes that merges the word representations and then computes a score. We'd also probably have another array which would actually store the representation for that tree, which is going to be used later on. But for now, let's just consider finding the maximizing value for the sum of scores. Next, we can move to trees of size 2. So this covered trees of size 1. Now let's look at trees of size 2. So for the tree that would, and by size 2 I mean the number of internal nodes. So these trees covered, a tree of size 2 would cover 3 words. So now imagine a tree that covers the first word, the second word, and the third word. What are 2 such trees? There's the tree which merges 1, 2 first, and then merges the representation of 1, 2 with the third word, or the other way around, merges 2, 3 together first, and then merges the first word with the result of merging 2 and 3. So the sum of the scores in this case would be the score of the first merge here, and then the new merge that corresponds to the root of this subtree that covers words from 1 to 3. So I already computed the merge of 1 and 2, that's A1, 2. So I can just take that score and then add the new score of merging, the result of merging 1, 2 with the third word, which is. So that's why we need the corresponding sorry, not word, but vector representation somewhere to reuse it in order to compute that score. So then I could compare that with the possibility of merging 2 and 3 first, and the score for that has been computed already. It's in this cell of the array. And then I would just add the score of then merging 1 with the result of having merged 2 and 3. And I'm assuming that I have that already somewhere. Then I can pass the word representation for 1, the representation for 2 and 3, and then again query my neural net to get a score, which would be this, and then add that to the value in the cell 2 and 3. And then I do a comparison, and then let's imagine that in this example, this subtree is actually more likely, then that's the value that I would keep in this array. And also somewhere I would keep what is the resulting vector at this node in that subtree, so I can reuse it later. Similarly, for the tree that covers words from 2 to position 2 to position 4, I have two possibilities. Either I reuse the subtree covering 2 and 3, and then I merge the result of that with the fourth word in the sentence, or I do the other way around, assuming I've merged 3 and 4 together, and then merging the result of that with the second word. And so similarly, say I do a comparison, maybe this is the most likely, the sum of scores that is highest, and so I store that instead in the array, and then also take the result of this merge, the vector representation, and put it somewhere so I can reuse it later. Now, if I reach that part of the array, then now I have to consider all the trees that cover 4 words. In this case, there's only one. So in this case, if we're covering 4 words, it can only cover from the first to the 4 words, so all words in the sentence. And then there are 3 possibilities. So what can I do? I can either assume that I have already merged all of the words from the first to the third position, and then all that's left is to merge the fourth word with my representation of the phrase from that covers word position 1 to position 3. So this would be the score of that subtree plus the new score from merging the fourth word with the representation of the phrase from 1 to 3, the cat is. And then I want to compare that with instead having merged 1 to 2 and also having merged 3 to 4 separately, and then just taking these 2 subtrees and joining them with a parent node and merging the representation of these 2 subtrees. So 1 and 2 and 3 and 4, they're here and here, so I can reuse those computations again. And so these cells in these arrays contain the scores of these 2 subtrees, and now I just need to increment the score of, incorporate the score of merging the representation of the phrase from 1 to 2, so the phrase the cat, with the representation of the phrase 3, 4, the phrase is here. And then finally, I can instead assume that I've merged already everything that's from 2 to 4. So I have, I take the best subtree I found for covering words at position 2 to 4, and then I add to this the remaining merge, which is to take the representation of the first word and merge it with the representation of the phrase from the second position to the fourth position. So now I have 3 things to compare. And now let's imagine that in this case, it's this option here that is most likely, that is assuming I've already covered 1 to 2 and 3 to 4, and then just merging these 2 subtrees together. And now in that case, if I then wanted to infer what is the syntactic tree that corresponds to that, well, in this case it would correspond to this syntactic tree. So indeed here we've made the decisions that we wanted to have merged use a subtree between 1 and 2 and join it with the subtree between 3 and 4. And then the subtree between 1 and 2, well, there's only one. It's the one that merges the first word with the second word. So it's that subtree. and then is here the subtree that the only possible subtree is this one, and here the decision I had made was to merge these two, so we get the global tree, which is like this. So that's a very simple example for this algorithm. I just wanted to give you an intuitive impression of how it actually works. For more details, I encourage you to look at the original Richard Socher paper and the references it contains to know more about how you could actually perform this for general length sentences. But effectively, the general procedure is you try to infer the best subtree for each possible span or phrase lengths, starting from phrases that cover 2 words, as in here, and then phrases that cover 3 words, as in here, and then phrases that cover 4 words, as in here. And by moving like this, you can always use the computations that you've performed previously for where you inferred the subtree that was best for these smaller phrases. Also, I'm not going to explain why, but this is actually not returning the best subtree. So this is actually an approximation of the best tree, and I encourage you to think more about this and to see why you might have to look at the original algorithm that's used for performing syntactic inference in syntactic parsing. But for now, all you need to know really is that this is the general procedure that is used with recursive neural networks for inferring the syntactic tree structure of a given sentence.